Okay, this is warm-up number 3. This is 2015-2016 Math Accounts book. A shift consists of rotating a two-digit number 90 degrees clockwise and then exchanging the position of the two digits. How many shifts must be performed before the number 19 returns to its original orientation? So mostly the hard part in this is just knowing what a shift is. So I have 19, it looks like that, and then after a shift I get a number that looks like this. I've rotated the 9 clockwise, and I've rotated the 1 clockwise, and I exchanged their positions. And then I can shift that again. I change their positions, and I rotate them both clockwise, so it looks like that. And then I do it again, because it's not quite there. Looks like this. And then I do it again, and voila, I get it back to 19. So that is 1, 2, 3, 4 shifts. Population Reference Bureau reported a net gain of 155 people on Earth each minute. At this rate, how many people are there on Earth each day? Okay, I like to do this. Just look at my units. I have 155 people per minute. And I want to know how many people a day are there that are born, so or that exist on the Earth. Let's see. I know that in 1 hour there are 60 minutes. In 1 minute, or excuse me, I'm sorry. No, in 1 day there are 24 hours. And so if I look at my units, my minutes cancel, my hours cancel, so that gives me people per day. So I'm doing 155 times 60 times 24. If you do that, you find that it's 223,200 each day. Here I have 1 over x 4 times is equal to 24. I'm going to simplify this to 4 times 1 over x equals 24. Or 4 over x equals 24. Do this how you like, but I like to think about it as cross multiplying in this way. So 4 is equal to 24x, and then divide both sides by 24. So x is equal to 4 over 24. So to simplify that, that's 1 over 6. Maxima wrote down 2 rows of numbers as shown. In the first row, we wrote the positive multiples of 7. Let's see, and on and on. Second row, positive multiples of 13. How many times did the corresponding terms in the first and second rows have the same units digit? All right, well, we already see one right here. Those two numbers have the same units digit. We want to know if between 7 and 70, are there other, and 13 and 130, are there other places where it has the same units digit? So I'm just going to repeat what he has here, 7, 14, 21. Yeah, I'll go ahead and repeat it. 28, 35, 42, 49, 56, 63, and 70. I'm only going to go up to 70 because then it starts repeating, right? Because then I have 77, 84. Notice the units digits are repeating, so I don't need to do that. Whatever I have, I'm going to have it repeated 10 times because I'm going up to 700. Okay, and similarly for 13, I have 13, 26, 39, 52, 65, and as we already know, we have 2 that are there. And then beyond that, I have 78, 91, 104, 117, and 130. Okay, so I also have shared units digits there. So that means for every 10, increment of 10, I'm going to have 2 sets of numbers that share the same units digits. And since I have 10 of these, that's going to give me 20 times. Because I'm going from 7 to 700, 7 goes into 7, or rather I have 10 sets of these numbers all the way up to 700. Okay, so in the 6 by 6 array of squares shown here, 2 squares are adjacent if they share a side. What is the probability that 2 adjacent squares chosen at random are not the same color? Express your answer as a common fraction. Well, in general, when I'm looking at probability, I'm looking at favorable outcomes. divided by the total number of outcomes. So I first want to figure out what are my favorable outcomes. That is, when do I have two adjacent squares that are not the same color? So if I have corner squares, these squares, I have four possible options. I have this square, well, let's see, is that right? Four for corner squares. Hold on, let me pause for just a second. Okay, sorry about that. So I'm looking at the favorable outcomes divided by the total outcomes. Now, first looking at the favorable outcomes for the corner squares, how many times do corner squares have different colors or not the same colors? Well, look, I have one occasion there, I have two occasions there, three, and four occasions. So for the corner squares, I have four. I'm going to put this in parentheses. This is for the corner squares. All right, and then I also have to consider the middle squares. And if I think about these, I have those are different colors, 2, 3, 4 that are different colors, four sets of adjacent squares that are different colors, and then I have four of these center squares. So that's going to be 16 for the middle squares. Those are the total number of possibilities for sets of adjacent squares that have different colors. And now I want to figure out what is the total number of possibilities, different colors or no. Well, again, with the corner squares, I have 1, 2, 3, 4, 5, 6, 7, 8 possible sets of adjacent sides. So for the corner squares, I have 8. For the side squares, eraser, there we go, let me erase this. How many sets of adjacent squares are there? Well, let's see. For this square, I have 1, 2, 3 adjacent squares. So I have 3, 6, 9, 12. So for each side here, I get 12 sets of adjacent squares. And I have 4 sides, so that's going to be 12 times 4, 48. All right. Now, that hasn't considered the middle squares. Now, if you're thinking, oh, he's overcounting these squares, hold on just a minute. I'll show you what I'm doing. If you're thinking that, if not, don't worry about it. Okay, now I'm looking at the center squares. For each of these squares, I have 1, 2, 3, 4 adjacent squares. So I have 4 sets of adjacent squares. And then here in the middle, I have 16. So that means I'm going to have 4 times 16. That's 64. That's for the all the squares in the middle. So that's 20 divided by 120, which simplifies down to 1 over 6. So that means I have a probability of 1 over 6. But in each case, I've been double counting squares because I'm double counting the adjacent sides. So I was actually going to have a probability that's half this. So my, or rather that's twice this. Excuse me, that's twice this. So my probability is going to be 1/3. And that's the answer. All right, number 26, a very round number is a positive integer that has exactly one non-zero digit. How many integers less than 1 billion are very round numbers? Well, a very round number is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's one set of very round numbers. And then we have 10, 20, all the way up to 90. And then we have 100, all the way up to 900, 1,000, all the way up to 9,000. Probably see where I'm going here. 10,000, all the way up to 90,000, 100,000, all the way up to 900,000. 1 million, all the way up to 10 million. or excuse me, to 9 million, and then 10 million, up to 90 million, and then 100 million, all the way up to 900 million. And then the next set would be starting at 1 billion. But since I'm looking for integers less than 1 billion, I'm not counting this at all. So I have 9 sets of 9 integers. That's going to be 9 times 9, or 81 is the right answer. Adding 3/8 to a number increases it by 5% of its original value. What is the original number? So 5%, that's 5 over 100, of my original number is equal to 3/8. So I need to solve this for x. So x is equal to 3/8 times 100 over 5. Let's see, that is 300 over 40. That's 7.5. What is the height of a rectangular prism with a length, width, and volume as given? Well, 4 times 3 times the height is equal to 108. So that height is 108 divided by 12. And 108 divided by 12 is 9. All right, Miss Swift wrote 40 pages of notes, each contain 240 words, and then I have these two typists that can type at different rates. If the two typists working together begin typing the notes, how long will it take them to finish it? Well, the first typist can go at 36 words per minute. And to find out the total number of words that she can type, we just multiply that times the number of minutes. The second typist can do 54 words per minute. We multiply that times t to get the total number of words. And then the total number of words that they need to type is 240. That's the number of words on each page times the number of pages. So let's see, I'm going to solve this for t. I'll leave you to do the algebra, but it's going to look like this. 240 times 40 divided by 36 plus 54. That's going to equal to t, which is going to be 107 minutes. And an exponentially talented salesman sells 1 car on his first day, 2 cars on his second day, 4 cars on his third day, and so on. So that every day after the first, he sells twice as many cars the day before. How many days does it take him to sell a total of at least 1,000 cars? Well, it doesn't take him that long, so let's just write out the answers, or the number of cars that he sells on each day. That's 1, 2, 4, 8, 16, 32, 64, 128, 256, and 512. It's probably going to be enough. You can add these up. Keep adding them until you get to 1,000. And you'll find that at this point that this equals to slightly more than 1,000. I forget what it is exactly. But anyway, so it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days to sell at least 1,000 cars. It's probably good. You could work that a slightly different way, but this is probably the simplest just because it doesn't take that long to get up to 1,000.